Here is a healthy production architecture. 4 microservices written in Go are effortlessly handling 2,000 requests per second, executing queries against a central Postgres database with sub-millisecond latency. This timeline shows what happens when that central database undergoes a brief 5-second outage. A planned maintenance window or a rapid failover event triggers a tiny disruption. But instead of recovering, that minor blip triggers a 10-minute system-wide cascading failure. During the actual 5-second window when the database is offline, the system behaves exactly as designed. In-flight queries fail, existing connections go stale, and the application correctly throws transient errors back to the client. But look at the timeline the exact moment the database comes back online. Instead of gracefully recovering, the application generates a massive self-sustaining load spike that tears the architecture apart. The code running on these servers is completely correct. This catastrophe is an emergent property of how perfectly correct components interact during a transient failure. If you inspect the database logic inside these Go microservices, you will find standard production-ready code. It handles context propagation, parameterizes queries to prevent injection, and gracefully wraps errors. The database connection pool is configured exactly as standard documentation dictates. Each pod is instructed to maintain a maximum of 25 open connections to the database. In a sterile environment, this implementation satisfies all linters, passes every test suite, and delivers excellent performance under steady-state load. Standard tutorials and AI generation tools write logic for a static world. They assume the underlying infrastructure remains predictable and stable. This lint-perfect configuration ignores system dynamics. It does not account for the backlog of requests that queue up during an outage, nor does it model the physical reality of how a database recovers its memory state after a restart. A system can be composed entirely of flawless, correct components and still destroy itself when subjected to the chaotic environment of a real production deployment. When the database goes down for those 5 seconds, the Go pods are immediately cut off. Within milliseconds, hundreds of active Go routines are left stranded, stacking up and waiting for a connection to execute their queries. Watch exactly what happens the millisecond the 5-second outage ends and the database begins accepting connections again. All 4 pods detect the database at the exact same instant. Because their internal queues are full of waiting Go routines, all 4 pods immediately request their absolute maximum of 25 connections, triggering 100 simultaneous TCP handshakes in under a second. This specific architectural failure pattern is a thundering herd. Multiple consumers detect resource availability simultaneously and blindly rush that shared resource all at once. The Go database driver has zero global awareness. It knows only about its own local connection limits and its own queue of waiting requests. It has no visibility into the fact that 3 other pods are hammering the database simultaneously. By strictly adhering to its local configuration, the application weaponizes the cluster against the newly recovering database. Establishing the 100 TCP connections is only the initial wave. The instant a connection is established, the backlogged Go routines immediately fire their queued SQL queries. This diagram compares the physical state of the database's memory. Before the outage, frequently accessed tables and indexes were cached in the shared buffer pool, allowing queries to execute in memory. After the restart, that memory is completely empty. The system is now suffering a cold cache penalty. Because the buffer pool is empty, every single incoming query from that thundering herd is forced to bypass memory and execute slow, physical disk reads. Queries that normally execute in 5 milliseconds now require over 800 milliseconds to complete. That is a 160 by latency degradation. Because each query takes 160 times longer to process, the database connections are held open 160 times longer. Total throughput drops to a crawl. The application is demanding maximum performance from the database at the exact second the database has zero cached capacity to provide it. With database throughput severely restricted by the cold cache, the internal request queues on the Go pods rapidly fill to maximum capacity. The incoming HTTP requests waiting in this queue eventually hit their hard 5-second execution timeout, returning a massive wave of 504 gateway errors to users. This map displays how the Kubernetes orchestrator monitors the health of the cluster during this slowdown. It periodically sends a small readiness probe to the pod to verify it is still alive. The application uses the identical connection pool for both heavy application queries and the orchestrator's health check. The small health check packet gets stuck behind a massive wall of application queries waiting for a database connection. The health check times out while waiting in the queue. Kubernetes misinterprets this timeout, falsely assuming the pod itself has completely crashed. Acting on this false signal, the orchestrator aggressively deletes and restarts the supposedly failed pod. The newly spun up pod boots with an empty queue, instantly requesting 25 brand new connections. It launches a second thundering herd directly at the already struggling database. This localized restart dumps more load onto the database, increasing query latency further. That causes the health checks on the remaining pods to fail, triggering a cluster-wide wave of identical restarts. Kubernetes has created a positive feedback loop of destruction. The orchestrator's automated recovery attempts turn a temporary slowdown into a self-reinforcing outage. This requires manual human intervention to stop. To engineer a resilient system, we must sever this orchestration loop. We start with the absolute highest priority intervention required to stop the Kubernetes death spiral. The critical architectural mistake was forcing lightweight liveness signals to share a connection pool with heavy application queries. The primary code fix is creating a completely separate, dedicated single connection pool exclusively for the health check endpoint. Even when the main application pool is utterly gridlocked with slow queries, the health check retains an independent lane to ping the database. The orchestrator now receives an accurate liveness signal. Kubernetes recognizes the application is simply slow rather than dead, and halts the restart cascade entirely. The highest leverage fix was not about making the database faster. It was ensuring the orchestration layer stops acting on false telemetry. With the orchestrator stabilized, we address the application pods themselves to prevent the synchronized connection storm from overwhelming the cold cache. This timeline illustrates the impact of jitter. Jitter is a random delay injected into the connection creation phase of each pod. By randomizing the reconnection timing, jitter transforms a vertical cliff of simultaneous connections into a manageable, staggered trickle that the database can easily absorb. The final architectural defense is a circuit breaker. By monitoring error percentages, the circuit breaker proactively drops application requests before they reach the database, protecting the vulnerable resource. During recovery, the circuit breaker allows only tiny probe queries through. This controlled flow warms up the database caches incrementally before fully opening the floodgates. The application is now resilient. The architecture is decoupled, protected from localized spikes, and capable of gracefully managing its own recovery. True production engineering requires anticipating and orchestrating exactly how individual components interact when the system inevitably breaks.